Just one thing about the concept presentations before we start again. So the order will be the same that was written on the program, but just two variations. First one is that after Laura Moschini, there will be Anna Maria Rovello, and after Utpal Sarkar, there will be Adriano Strucchi and Pauline Lizet, and Alessio Spaccini will be the last Alessio. Where is Alessio? Was here 5 minutes ago. Okay. So, do you want me to write the order on the board, or for the interested people remember it? Signs of life? No signs of life. Okay.
Okay, so welcome back. We have our last presentation for the astrophysics and cosmology section by Stefania Condotti, who will tell us something about dark energy.
That was simpler than the subtitle. That was the title.
Dark energy coupling with electromagnetism as seen from future low medium redshift probes.
Something. So hi everybody. So I'm gonna skip the out. This is manual, right? It's like. Yes. Oh, okay. I thought it was. Yeah. Okay. So hi everybody. I will skip the outline and blah blah and go directly to what I'm going to say. So this is, at the best of our knowledge, this is basically the content of our universe, the energy density content of our universe. And you see that basically what we know for sure is the only 5%, so it's the ordinary matter. And then there is 27% of a component called dark matter that is the principle responsible for the structure that we see today in the sky. And basically the rest, 70% more or less, is a component called dark energy that we don't know either, so we call it dark as well. That basically is a 2/3 of the energy density of the universe, and it's the principle responsible for the acceleration of the evolution of the universe that we see today, looking at the sky. So how do we get to this view? Well, there is a lot of observational probes that we can use in order to picture this this content of the universe, and you can see that all together they point to the so-called cosmic concordance model. And this is a good news because there was a time in which there was no consensus whatsoever on the content of the universe. And basically, this concordance model is, again, made up of, so this is the omega matter, that is the energy density in matter in general of the universe, and this is omega lambda, that is a parameter telling you how much energy density of the dark energy is. And so altogether, they seem to agree in one point, basically. And this cosmic concordance model is called the lambda CDM for the reason that I just told. As I was saying, we observe the acceleration of the evolution of the universe, and historically, the evidence for this cosmic acceleration came from type 1a supernovae. And supernovae are, as you may know, maybe probably now, are very bright sources. And with very bright, I mean that this is a supernovae, this is the host galaxies, and you can see that they are of comparable luminosity. Plus, they are very distant, and plus they are standard candle. Standard candle means that we know basically their intrinsic luminosity, more or less. And knowing their intrinsic luminosity, measuring their apparent luminosity, basically we can get their distance. That is called the luminosity distance for this reason. In 1998, two different groups of cosmologists found out that by observing type 1a supernovae, find out that they were not compatible with the model for the universe, which contained only matter. That is this one. Rather, they were compatible more with the universe that were filled with the dark energy. And the reason for that is that as the universe expanded slower in the past, a universe filled with dark energy expanded slower in the past, the distance that the light has to travel coming towards us are greater towards us. So you will expect fainter supernovae in a dark energy dominated universe. What we know for sure, or what we think we know about dark energy, basically, again, it leads to acceleration, has a negative pressure, smoothly distributed and invisible, doesn't clump into galaxies like the matter or dark matter, constitutes the 2/3 of the energy in the universe, and the simplest model for it is the cosmological constant. Well, what is the cosmological constant? In order to tell you this, I have to tell a story. 1917, basically, Einstein applied for the first time his general relativity to cosmology, and he was looking for a model of the universe that was closed and static, because that was his belief about our universe. But the general relativity was in contrast with the cosmology, because basically the universe would have recollapsed on itself. And so he added a term, a constant term, called lambda, that basically prevented this recollapsing of the universe, this recollapse of the universe. And it was, of course, in agreement with its general relativity equations. Then in 1922 and 1927, Friedman and Lemaitre proposed a universe in which there was an expansion without the cosmological constant, without the use of cosmological constant. Well, Einstein did not take it very well. This is his comments to their paper. And you can read the first one, and I can translate the second one. This is French, I'm not daring to pronounce it. But basically, I can translate. Your calculations are correct, but your physics is abominable. True story. In 1929, then Edwin Hubble basically find the evidence for the galaxies, basically find the evidence that the galaxies were receding away from us. And the greater the distance of the galaxy, the faster it was receding from, it seems to receding from us. This is basically can be written in this simple formula, in which this is the velocity of the galaxy, this is its distance, and this is a term that now we call the Hubble constant, and this is calculated today, so each knot is today. At that time, he calculated that each time would have been like 500 kilometers per second per megaparsec. But now that we have much better refined measurement, we can say that probably it's around 70 kilometers per second per megaparsec. Basically, this provided the evidence for the expansion of the universe. And so Einstein gave up with his idea of a closed and static universe and called the cosmological constant his biggest blunder. And then we are back in our days, and then, which I told you in 1998, the two groups find the evidence for the expansion of the universe plus the acceleration of the expansion of the universe. And in order to recover this acceleration, to explain this acceleration, then Einstein's cosmological constant was resurrected. So Einstein was right, even when he thought he was wrong. Eventually, in 2011, these three guys that were the PI of the two groups, the Supernova Cosmology Project and the high-sec supernova search team, got the Nobel Prize. But this, of course, is not the end of the story, because the cosmological constant, while is explaining this acceleration very well, has at least a couple of theoretical problems. So the first one is called fine-tuning, and this is related with the idea that if you want to give a cosmological, physical explanation to the dark energy, to the cosmological constant, you may want to link it with something that is constant, that is filling the universe homogeneously, and provides a negative pressure. So basically, the simplest thing to think of is the vacuum energy. But if you calculate the energy density of the vacuum energy in quantum field theory and you compare it with the value that should have in cosmology, you have a big problem. A problem of 123 orders of magnitude. The second big problem of the cosmological constant is called the why now, and basically states that even if omega matter and omega lambda have a ratio that is rapidly changing with redshift, now are a comparable size at present day. And this is pretty strange, unless invoking some anthropic principle. And so you may ask, why now? So these theoretical issues basically brought to the formulation of many different alternatives models. The most famous and used one is called quintessence. Quintessence is basically an additional energy term driven by a scalar field, which has a potential that determines basically the dark energy properties, like the evolution of the equation of state parameter and the sound speed, etc., etc. This new component will have an equation that in general you can write like this. So this is the equation of state parameter, that is the ratio between the pressure and the energy density, and you can basically write it like this very generally. This is the potential, this is the kinetic term. Even if you don't have your preferred dark energy model, you can do a very smart thing, like to have a parameterization for the evolution of the dark energy equation of state parameter. And you can see that there are many different parameterizations. Basically, they want to mimic the evolution of the equation of state parameter with respect of redshift. This is the scale factor, but basically it's the same. In what follows, we will use the CPL parameterization that is very simple. Basically, it's a Taylor expansion, and it has only two parameters, W0 and W1, or WA as you want to call it. CPL stands for Chevalier, Polanski, and Linder, if you want to know. And basically what you want to do is to put constraints on these two parameters in order to detect some insight of deviation from the lambda CDM cosmology model that has W0 equal to -1, and that's it, WA equal to -1 and constant for the redshifts. The current constraints are the following. This comes basically from cosmology. This is WMAP, this is Planck. You can see that basically the CMB is pointing towards cosmological constant, but then if you add many different external data sets, you have a shift towards dynamical dark energy. But more or less, they are pretty compatible with the cosmological constant. Then, to test dark energy, we need probes that are sensitive to expansion parameters. We are starting with supernovae, as I already told you. The supernova probe dark energy evolution through the luminosity distance. And this is the evolution of the universe in the case in which you have a dark energy parameterized with CPL parameterization. Just a formula, don't worry. Then redshift drift. I will spend a couple of slides on this pretty new observable. Basically, the redshift drift is a direct measurement of the temporal change of the distant source's redshift due to the expansion of the universe. Basically, what you do is you take a distant source, you measure its redshift, then you wait 10, 20, 30 years, and then you do it again. The difference of the redshift is basically can be rewritten in a difference of the spectroscopic velocity, and it can then be tied to the evolution of the universe. Because basically this redshift difference is due to the expansion of the universe. This is the case of a cosmological constant, and this is the case of something else that is not a cosmological constant, and again, it's parameterized through a CPL parameterization. What you basically want to detect is a departure from the evolution of the expansion rate, that is this one, compared to the simple lambda CDM model. Why we should care? Well, for a couple of reasons, well, more than a couple, because it's a direct measurement of the expansion of the universe, is based on well-understood physics, probes a redshift range in which there are no other cosmological probes, between 2 and 5, does not need any other underlying theoretical assumption, and it will be feasible. That is the most important thing, I think. This is just a slide to tell you that you can do something pretty decent with the redshift drift, joined with CMB. Don't worry about the details. What I want you to notice that if you use the redshift drift plus the CMB, you will have a pretty decent constraints on these parameters, so W0, H0, and omega n. This is pretty good constraints compatible with other joint constraints. And this is mainly due not because of the better sensitivity of the redshift drift that you can see in red, it's not very good, but the good point is that it has a different direction of degeneracy in the parameter space. So basically, when you use it in conjunction with CMB, you get this tiny constraints because of the different direction. Basically, it cuts down the parameter space. Then, a couple of slides on the last observables of the dark energy, that is the gravitational lensing. Stefano already mentioned a bit, but I will just repeat it a bit. This is one of the most famous picture from the Hubble Space Telescope. In 1995, the Hubble Space Telescope was pointed towards a really small patch of the sky near the Big Dipper. And it was able to see thousands of new galaxies. And these new galaxies sometimes appeared like stretched or squeezed. And this is not just because the galaxies by themselves are just this curious shape, but this is due to to gravity, basically, because you have to imagine that distant galaxies travel through space, and space is bent by dark matter and by matter in general. And so, as space-time is bent by matter, then the light from these galaxies are bent as well, and you can basically have this shape for a galaxy that is not a physical one, it's just a consequence of gravity. According to the different geometry that you can have, you can have many different results. So you are here, this is the observer, this is the galaxy cluster that has, but basically it's the lens, and this is the background galaxies. So according to this geometry, you can have multiple images, or arclets that are the squeezed galaxies, or you basically mostly have a weak shear that is just a very weak shear of the form of the galaxy. Statistically, what you can do is to measure the distortion of background images and try to reconstruct all the matter that comes from that is between your distant galaxies and the observer, basically us. And you can do it statistically. And this is the the difference between an unlensed image and a lensed image. You reconstruct statistically the shear of these galaxies, and you can basically reconstruct all the matter that is between us and the distant galaxies. So now we have all these observables. I'm fine. What you can do, basically you look for either deviation from W minus 1, or you can look for clustering of dark energy. What you can do is to look, a smart thing, you can look to coupling to other sector of the theory, like for example, electromagnetism. So basically, you are looking for a time evolution of physical constant, like for example, the Feinstein constant. This is a very general formula that says that if you have dynamical dark energy here, this can be coupled with the electromagnetic field with this zeta parameter, that is strength of the coupling, and you will have an alpha variation. This is basically what I told you. If the dark energy is explained through a scalar field, then it's reasonable that is coupled to the electromagnetic field. And you are basically looking for distinctive signature in your cosmological observables. I can skip this. This is just to let you know that it's true. So if you choose two different energy models, dark energy models, you have two different signals. I will skip this. You will need alpha probes in order to constrain the variation of the fine structure constant, and I will go directly to the results. So basically, this is, we assumed a fiducial lambda CDM model in this case. So no alpha variation, you have W0 equal to -1 and W8 equal to 0. So this is cosmological constant. You assume this fiducial lambda CDM model, and you build a mock data set given by all, means supernovae plus weak lensing plus redshift width plus quasars. And the constraints are color-coded in this way. So the red curves are here, and it's in the case in which you consider all of this. And then you start by considering less and less data set. So you have all minus supernovae, all minus weak lensing, and all minus, the green one is all minus weak lensing and supernovae. So basically you can see here is the strength of the supernovae plus weak lensing combined data set, because the conjunction of the two is really narrowing down the parameter space in W0, WA parameter space, yes. You can see it also in one dimension. This is basically the same when you consider, when you are not considering weak lensing and supernovae, the constraints are really broad, while when you are considering all of that, the constraints are really, really narrow to -1 and 0, and also to omega lambda. What is puzzling at first look is this one. Basically, the red curve in which you consider everything is larger, so the constraints are broader with respect to the case in which you are not considering weak lensing and supernovae. This is something strange at first look, but if you consider that we consider a fiducial lambda CDM model, then the mystery is solved in this way. This is the formula. So you have delta alpha over alpha that in lambda CDM cosmology is 0. You can obtain this in two ways. Either you have W that is -1, and or you have zeta that is 0, and zeta is the coupling. So when you have the whole data set, so it's really narrowing down W to its fiducial value that is -1, then basically zeta can be whatever, because you will get anyway delta alpha over alpha equal to 0, and vice versa. If you consider that when W is not constrained at all, then zeta has to be really tight, close to 0, to have delta alpha over alpha close to 0 in a lambda CDM cosmology. Last slide. When you don't consider a fiducial lambda CDM cosmology, then the normal degeneracy are showing, are clearly showed, and you can basically obtain very, very good constraints on the W0 and WA parameters, and the constraints on W0 is a factor of 2 better than in the previous case. The constraints on WA is a 1 order of magnitude better than in the previous case. And this is basically due to the fact that you are using quasars that are constraining the alpha variation, and they have a different direction of the degeneracy again. So the joint constraints is really, really, really good. Conclusion, but I'm run out of time, so I think that's it.
Thank you. A question for Stefania?
Hi. I'm wondering which are the hypotheses you make in the way dark energy couples to electromagnetism? Because in general, I mean, if there is so the coupling is very, very constrained by collider physics, like very tightly constrained.
Of course.
So I'm wondering, I mean, you should make some hypotheses, no? Because it influences the alpha constant. On the other hand, you have to make sure that it does not produce strength signals in colliders. So I'm just wondering which hypothesis you make.
You are considering different scales. No?
Yeah, but this is already an hypothesis, right?
Well, it is, in a sense. You are not considering what is inside. So you're considering very big scales. So, you know, and I mean, okay. Apart from this, you are basically not saying why there is a fine structure constant variation. You're just trying to detect it. So what I'm trying to say is that two things. You have to consider that if alpha is varying, then you have another problem of explaining it. Okay? And basically what we do is a very simple thing. We just consider the coupling between the dark energy and the electromagnetism. But of course, this is a very, very simplistic case, because you should also consider the other couplings. So the couplings of the entire sector of scalar fields, because you cannot think that it's not coupled, for example, with the strong field, for example. But these are different scales.
Yes, but I mean, why should you make the hypothesis that the coupling depends on scale? So strong.
Because so strong is that the
Changes
well,
strong,
what?
I mean, it changes quite a lot because in some sense it has to be on small scales, it has to be negligible, but it has to be observable on very large scales. So it's not a tiny change, no?
Well, it's the order of what, a couple of parts per million.
Still, I mean,
Yeah, I mean, there is a controversial evidence for the variation of the fine structure constant during time. It's not during, I mean, it's not considering scales, it's during time. So the change in ratios is not the change in scales. So the change, the alpha variation is in ratios, so in time.
yeah, I understand.
So maybe I don't get maybe we can talk later, because I don't know if I get your point.
I mean, my only point is that if you try to estimate the parameters, no?
Yeah.
Of the dark energy,
Yes.
should make some hypothesis how dark energy influences electromagnetism. Should do something.
Yeah, yes. I mean, yes, but it's, I mean.
No, I just wanted to understand which are these hypotheses you make.
Well, this formula is truly general. So this is the variation of the dark energy, no? This is the coupling, the strength coupling, and you will get the alpha variation. Very general and very phenomenological, I would say.
Yeah, I mean, my problem is that you don't see in that formula how this mechanism behaves, no? Coupling. That's the reason of my question.
Yeah, so physically, I'm not sure.
Well,
So
maybe we
for a
can
second,
discuss later because
yeah, sorry.
Yeah, I think we're running.
Okay. One very quick question.
Very good question.
Yeah, my question is somehow related to this question, because in the end, if I understood correctly, your results will let omega dot is 0 and omega dot is 0 and omega 0 is -1. So in the end, you
No, yeah, but this is done for future cosmological probes. So you have to assume a
yeah,
fiducial model.
you're seeing physical skills. So
We are assuming two fiducial models.
yeah, see that model and that one. So in the end, your results show that omega dot is -1.
These are future, so you are making MOX catalogs. So you are constraining how well a future experiment will do about these parameters. You are not saying, so you are assuming a model. You have to do it because otherwise you don't have real data. You have to build it. So you have to assume a cosmological model and say how good your future experiment will do about that model. Of course, it's a model dependent because if you assume a lambda CDM, you will get some results. If you don't assume a lambda CDM, you will get other results. But it's basically a measure of how performing will be your future experiment.
Okay. Okay. So let's thank Stefan again. We move now to the poster session.
Okay. Okay. Now we can start the poster session with Leda Luciantini from Pisa University. She tells us about quantum quenches from excited states in the iso chain.
I changed the title. Sorry. Okay. Thank you.
Please send here. Okay.
Thank you. My name is Leda Luciantini, and I'm a second-year PhD student at Pisa University. And my research interest is in the condensed matter sector, in particular from the theoretical point of view. And what I study is the evolution from an initial out of equilibrium state of isolated many-body quantum systems. So the simplest way of putting a system out of equilibrium is through the so-called quantum quench, which is a protocol that consists in suddenly varying one of the parameters of the Hamiltonian, and then, for example, at t equals 0, you change the parameter lambda to lambda prime, and then you let evolve the system unitarily under this h of lambda prime Hamiltonian. So the main questions we want to address are, does the system then evolve to a new equilibrium state? And if so, which is the statistical example that can represent it? And also, for example, how do entanglement entropy or also local observables evolve in time? So, what I did in this first work is try to answer these basic questions by, let's say, using a model for h of lambda that is simplified. And it is the transversalizing chain, which is a model of a lattice model of interacting spins put in one dimension. They interact via nearest neighbor interactions among themselves, and are also subject to an external magnetic field transverse to the previous direction. So, in this case, the quench consists in a sudden change of the intensity of the magnetic field. And despite the simplicity of this model, it is a very interesting one because let's say that it is on one side a paradigm of quantum phase transition, and on the other side it also allows an analytic description. So this is what I will talk about, what I described in my poster.
Next speaker is Luca Costantin from Padova University. He will tell us about the intrinsic shape.
The slides are following, so if you open that and just go to the next one, that should be
The intrinsic shape and formation of bulges in lenticular galaxies.
Hey everybody, my project is about the intrinsic shape and formation of bulges in lenticular galaxies. And the definition of our bulges is the extra light in the central region of a disk. And there are various types of bulges. The two big families is about classical bulges and disk-like bulges. And classical bulges are similar to low brightness elliptical galaxies, whereas disk-like bulge is similar to a disk. Different scenarios have been proposed to explain in which way a bulge is formed and a galaxy is formed. And we have two types: rapid merging, as in classical bulge, and slow, as a cyclic evolution in disk-like bulge. The point to keep in mind is that different types of bulges and different scenarios can coexist in the same galaxy. For what concerns the kinematic of the bulge, we have classical bulge in which we have random motion, whereas in disk-like bulge we have rotation motion. And this is what we observe in the sky, a two-dimensional image. And what I did, I performed a two-dimensional photometric decomposition of the galaxy in order to obtain the photometric parameters of the galaxy. And then I have made a statistical analysis because, of course, the bulge, the galaxies, is three-dimensional. And this is the intrinsic shape. And by coupling the intrinsic shape that I did in my work and the dynamical structure of Atlas example of S0 bulges, we are testing if the bulges in the galaxies are axisymmetric or non-axisymmetric in accordance with prediction about the formation of different bulges in different galaxies. Thanks.
Next speaker is Matteo De Benassuti from Rome University, La Sapienza. He will tell us about decoding the stellar fossils of the dusty MW progenitors.
Hi everyone, I'm working at the Observatory of Rome on the chemical evolution of the Milky Way galaxy. So if we want to understand why the universe we observe today is the way it is, it appears, we have to go back in time, down to its first chemical enrichment stages. But the more we go back in time, the less we know about the physical processes leading the evolution. So we observe that the universe is built up from mainly by low mass stars, which form in star-forming region, which have been enriched by the first supernovae in both metals and dust. And these supernovae were produced by the first massive stars. And so this is what we observe, and this is what we would like to know. But such stars are have not been observed yet. So we can just use some models and to match the observed properties of the Milky Way galaxy. So we have to do some kind of stellar archaeology and looking at the oldest stars in our galaxy, which are located in the Milky Way halo. And we want to explain why there are some stars which have a very low iron content, which should be the oldest stars because they have very low abundances. So we have a semi-analytical model which reproduces the chemical evolution of our galaxy, and we compare our results with the so-called metallicity distribution function of the Milky Way halo, which is the number of stars with respect to the iron content. So if we consider the total number of stars, we can constrain the initial mass function of the first stars. And if we do a step forward and we look at the abundances of other elements, such as carbon, we can also constrain the transition of the universe between the formation of massive stars to the formation of low mass stars. Okay.
Speaker is Yan Chen from CISA. He presents his work about structure and morphology of massive galaxies at high redshift.
No,
okay.
let's go to the next.
Hello, I'm representing Lulu Fan on structure and morphology of X-ray selected active galactic nucleus hosts at redshift 1 to 3 with Hubble Space Telescope observation. So our motivation is to study what triggers HN activity. Is it a major measure or some secular mechanism? We have a sample of X-ray selected agent hosts and the control sample of non-active galaxies. So for each host galaxy, we selected 10 non-active galaxies with similar stellar mass and redshift. Then for this galaxy, with Hubble's high resolution image, we can study the morphology. For example, this galaxy looks very regular and smooth. So we classify it as class 0. From this image, we can measure some parameters of which describe the relative flux distribution within the galaxy. So is it smooth or it is concentrated? And we can also fit some analytical model to the galaxy as shown in this figure, and then we can subtract the model from the original image to get this residual image. So basically you can not see residuals. And for this galaxy, it's class 1 with a companion galaxy, and there is some residue. And here is an example of class 2 system with 2 merging galaxy. The profile is strongly distorted, and you can see a lot of significant residue. So our results are shown in these figures and the table. Statistically, we cannot see a difference between the agent sample and the host under control sample. So our conclusion is the major measure are not necessary for triggering the agent activity, and the secular interaction could play a crucial role in triggering agent activity and the evolution between host galaxy and the black hole. Thanks.
Speaker is Luca Giovannelli from Rome University Tor Vergata. He presents his work about optical test of the Lutin Fabry-Perot prototype.
Thank you. So I will present this prototype. When I started my PhD program, it was a design paper, and now more or less is a functional prototype. Fabry-Perot interferometer is a very narrow band filter, optical filter, which is based on optical cavity, which has to be controlled in a nanometric control system to control the parallelism and the distance between two semi-reflective plates. And in this way, we can achieve a very high resolution spectrograph, which is able even to take images. Last few months, I obtained some data on this prototype about its spectral stability over several hours, and it has been proved to have a drift of about less than 1 picometer over 1 hour, and it has a bandwidth of about 8 picometers. And we also performed an optical qualification at the Istituto Nazionale di Ottica in Arcetri of the two optical plates, and we measured the surface errors and providing the qualification of the surface to be about lambda over 80, so an error of about 9 nanometers over a surface of 23 millimeters of diameter. So for the future, the idea is to put this kind of instrument on a satellite, which should be devoted to the study of solar atmosphere dynamics. We hope to be funded for that. So, thank you.
Next speaker is Lara Moschini from Padova University. She tells us about one neutron transfer reaction, a 1D toy model.
Hi everybody, I'm Laura Moschini. I am a first year PhD student at universities of Padova and Sevilla, and my field of interest is theoretical nuclear physics. We are developing a one-dimensional toy model to describe one neutron transfer reactions. They are very useful tools to study the nuclei structure. So, what is a nuclear transfer reaction? It is the peripheral collision between nuclei with the transfer of one or more neutrons or protons. And here you have this scheme. It is an example of a DP reaction that is an ion is incoming, and it takes a neutron from a deuterium, leaving a proton. Our model describes the two heavy ion collision, and you can see two potential wells, one for the target and the other for the projectile. The neutron initially sits in the target, and this is the probability to find it. We provide a time evolution, and the projectile is approaching to the target, and at a certain distance there is the probability for the neutron to be transferred. Then, at a certain distance, when the projectile reaches the distance of closest approach, the two nuclei partially overlap. They do not fuse completely because this is a peripheral collision, and the two nuclei maintain their identity during the collision. Then the projectile comes back, and at the end, when the projectile now the projectile is far enough, so we can measure the transfer probability. What if you are curious about this transfer probability and about on which parameters it depends, you can see my poster, and then we'll answer your questions.
Next speaker is Anna Maria Novello from Geneva University. She tells us about charge density waves in COX TI-SC2.
Thanks. I'm Anna Maria Novello from University of Geneva, where I'm doing my PhD. And today I would like to present you my measurements on copper intercalated titanium diselenate. This material is a transition metal dichalcogenase, and this means that, like graphite, for example, it can be exfoliated to obtain one layer. One layer of this material is made by a transition metal titanium, that is blue in the picture, that is octahedrally coordinated with selenium atoms. And this layer then is weakly bound with the next one through van der Waals forces. And in between the layers, it's possible, for example, to insert foreign species, like in this case, copper. This material is interesting for physics because it's a highly correlated electron system, and it exhibits a transition to charge density wave. And when we add copper in the structure, this material becomes also superconducting at low temperature. This, as you can see from the phase diagram, this material is quite similar to high-TC superconductors, where you have a pseudo-gap phase. And in this field, it's really important to try to understand where this pseudo-gap phase comes from. Our idea is to study a super system, in this case, titanium diselenate, to have an idea how superconductivity is working. And this material is also interesting for application, maybe one day. And these layer systems are already used to make transistors still in the lab. Hopefully, one day we'll have real transistor made with this material. So it's important for electronics, but it's also important because, as I said, there is a possibility to better understand superconductivity. And superconductivity is already used in many applications, like, for example, magnetic resonance, power cables, and accelerators. So it's really important to understand how it works to hopefully have one day also superconductivity at even higher temperature. I'm doing my measurement with the scanning tunneling microscope, so I'm really studying what happened at the surface of this material. In my case, we are using a commercial system, and we are working in ultra-high vacuum. This means pressure that are lower than 10 to minus 9 millibar, and at really low temperature. We are working at 1.1 Kelvin. And then here you have some couple of images. Here is an example of the surface of this material at room temperature, and here it's after the transition to charge density waves. So you can clearly see the 2x2 reconstruction due to the charge density wave. Here you have atoms and defects, and here is the same surface, but you see that there are some atoms that are much brighter than the others, and this is the charge density wave reconstruction. And if you want to see what's happening when we add copper, please come to my poster. Thank you.
Next speaker is Uttal Sarkar from Assam University. He presents work about the electronic structure of graphene family.
Good afternoon, everybody. Myself, Uttal Sarkar. Now we will discuss about the tuning of band gap due to fluorination of graphene and graphene family. Our main aim is to increase the band gap of this graphene family. So we can do that one in two ways, either by doping by fluorine or by BN substitution, or by increasing the chain length between the two benzene rings. So that is my main aim. So here, this structure is basically graphene structure, and then we can increase this acetyl linkage. We will get graphene families, pristine system, of course, and then we can increase to modify this one is this way. Another way is that we can replace this acetyl linkage by the PN substitution or by graphite or by fluorine substitution. So these are the band gaps. The band gap for graphene family is increasing if we just replace this, if we just increase this acetyl linkage in between the two benzene rings. And this is the band gap for graphene family. This one, if we just put the fluorine at the chain side, and if we put the graphene in the ring side or in the whole region, the band gap will increase further. So if you want to see what is the main orbitals interacting here, please come to my poster. We'll discuss that.
Speaker is Audrien Staki from Geneva University. It allows about shining light on CUO for exploring ITC multiferroids.
Okay, good afternoon everyone. My name is Adrian Stucchi. I work in the University of Geneva in the Council Matter Physics Department. And the title of my poster is Shining Light of CUO for Exploring ITC Multiferroids. First question is, effectively, what is multiferricity? As the definition, we can say that a single phase can be defined as multiferric if two or more ferric primary ferric properties are united. In fact, we are more or less interested in magnetoelectric multiferric. That means materials where you can tune and control the polarization by applying a magnetic field, or inversely controlling the polarization, the magnetization by applying an electrical field. Industrial application could be imagined, for example, in spintronic devices. We are actually in the two-state logic in our computer, but from data storage computer, we can imagine with multiferricity, increase that with a four-state logic. In condensed matter physics, it's well accepted that a good result, the credibility of a result is strongly correlated to the quality of the crystal that we are using. So we grew our own crystal with two techniques. We use the optical floating zone in image furnaces and the chemical vapor transport method in sealed quartz tube. The both methods are giving us a very high quality crystal with large faces larger than a few millimeters square. According to this station here, we know that the physical properties of system can be characterized by the natural frequencies and the energy scales, and that's why we are also interested by the optical response of our sample. Concretely, we are just shining light on our sample, and we analyze the scattered or the reflected beam. We can use a large range of different facilities, for example, like polarization or magnetic field, low temperature, or even the high hydrostatic pressure to analyze the characteristic of the matter. So if you're interested to know how it's possible to grow crystal or what we can extract from the optical spectroscopy, I will be glad to explain you what I'm working on my book.
The speaker is Pauline Delceau from Porto University. She tells us about evolution of the fine structure constant in runaway dilaton models.
So hi everybody, I'm Pauline Delceau from the University of Porto. I'm presenting a poster about the evolution of the fine structure constant in the runaway dilaton model. So as Stefania explained before, she addressed a little bit my poster. So basically, we know that we have 2/3 of the energy density of the universe that we can't really characterize besides including a cosmological constant. And parallelly, we have some recent observation that suggests that the fine structural constant is varying in time. And here you have like the recent observation. And what I'm doing now is basically testing some cosmological model, including the variation of these constants, and see what will be the cosmological observational consequences. And the model that the model that my poster is presenting is a dilate and runaway model, which is a string-inspired model. And we are the work that we are doing is trying to find some prop to differentiate this model from the lambda-Schleisian model. And if you using the variation of the observation of the variation of that we have, we can actually put some constraints in the coupling that Stefania talked before. And here is an example of the variation of alpha on this model. As a function of redshift, considering some constant that we have in the model, and we can put some constraint on it.